the first lecture of the first unit, the Introduction to Calculus and an Introduction to Limits. So first question is, what is calculus? What are you about to learn? You're going to learn the math of change, or the math of infinitesimals. That's the two ways calculus can be defined. Infinitesimals, very, very small, minute changes. Infinitely small changes. Small lengths. And there are two major problems solved by calculus. One was finding the tangent line anywhere on a curve. Here's a curve. Quickly sketch it if you want to. We could pick any point. And then at that point on the function, calculus found a way to find the tangent line. Tangent line, if you remember from geometry, is just touching the function. Very, very hard problem. It was almost impossible for all generic situations until calculus was discovered. This is differential calculus. We will deal with this problem and applications of this problem in the first semester. We'll find that the slope of that line determines the instantaneous rate of change of the function at that point, at that exact moment. Second problem is finding the area or volume of an irregular shape. So irregular shapes just can come from a function, and we can just kind of set some boundaries, and all of a sudden we've created an irregular shape, and we can find the area of that shape. It's not a standard geometric shape, so we can't use, a formula, but we'll be able to find the area of that shape. This is called integral calculus. We'll deal with this in the second semester. Introduce you to the notation you'll see in the first semester. The instantaneous rate of change, or the slope of a tangent, is a derivative. This is the notation for a derivative of a function at a specific point. These are kind of like D's, but they're not. They're kind of like Greek letters, Greek D's. The Greek D is delta. This is kind of another kind of D, meaning something similar to what delta means. Over here, to find this area, we would say that the area would be, let's say this is A and B, be equal to, this is a tall skinny S, it's called an integral from A to B of f of x dx. And we will figure out what that notation means and what this notation means soon. But that's just introducing it to you. Before we go into these problems, we must learn about limits. Okay, so here's the intro to limits. That was intro to calculus. Limits are the building blocks of calculus. And before we start talking about limits, we're going to review function notation, just so you're cool with function notation, inputs and outputs. So here's a function. We're going to be using this example a lot, so go ahead and sketch it down. on a coordinate plane. So what we have is here is an x-axis and a y-axis. The x-axis is where we get our inputs to our function. If I take any x, plug it into a function, I get an output represented by a point. So all of this curve is represented by an infinite collection of points. And those are our outputs, our f of x's. They are y values. Okay? And the curve is just a collection of solid dots, an infinite amount of them. There is an open circle there. We'll talk about that in a second. Okay? But we would say that my function value, f at, let's say, 1, so this is the function value given the input of 1, or the x value of 1, is equal to, well, if I have an input of 1, my output, my function value at that specific location is 2. If I go and look at f of 4, that's saying the function value given an input of the value 4, that is 0. These are closed circles. They do not look like closed circles on the graph, but they are. It's just since we have so many of them, they kind of form together to look like that smooth curve. But they are closed circles there. Now, if we look at f of 3, since we have an open circle, we say that the function is not defined there. It's just at that location at 3, given this graph. But we don't have to deal with just whole numbers with functions, inputs, and outputs. I could just say f of, maybe 3.999. And if I looked at the input 3.999, what is my output or my y going to be? Very, very close to 0, but negative. Okay, that's something we have to kind of keep in mind, that we don't have to look just at whole numbers. We can look very, very close to whole numbers. And maybe that's the answer. Now, we don't have a function value at 3, but I'll tell you we will have function values really, really close to 3, like at 3.0001. Now, what would we think the function value is for the input of 3.0001? Well, it actually will be defined. We'll say that just the point at 3 is undefined, but just to the right of 3 is going to be close to what number? Yeah, it looks like it's going to be really close to -1, so it's maybe like negative 0.999 or something like that. Okay? Every single input will have a defined output, except in this graph at that specific spot over 3. Okay, so that's a review of function notation. Now let's talk about what a limit is. A limit is the value that a function approaches as the input approaches some value. Now, maybe I'll help you out by giving it an x and a y. A limit is the y value that a function approaches as the input approaches some x value. Now we know that f of 1 was 2. That is defined. It doesn't have a closed circle, but you can assume it is a closed circle since it is a continuous curve. We can also say that the function, or as x approaches 1, the function, I won't say the function, I'll just say f of x, approaches 2. Okay, my function value at 1 is 2, and the function is approaching that value at 2. But let's look at f of 3. I know f of 3 right now is undefined. But if I look to the left and to the right of this point right here that's undefined, I'll see that my function values are approaching this y value of -1. Well, that's the idea of a limit. We might not have a function value. It doesn't matter. We don't really care what's exactly here. We're just caring about what my function is trending towards as we're getting close to that specific input location. I'd say as x approaches three, f of x approaches 1. -1, sorry. Now we could have a situation where we might have a function and we have an open circle here, but we could have a closed circle above it. If that was occurring here, well, the only thing that would change is instead of f of 3 being undefined, we would say f of 3 is just the function value that's defined above it at 1. However, the statement below that is still true. Even though we now have a function value, f of 3 is equal to 1, as x is approaching 3, my function values are approaching -1 down here. Okay? We will use specific notation for what we just said, these statements. The notation is as follows. It's undercase LIM, stand for the limit. Underneath the LIM will be x and an arrow, and then some input value, some x value. I will use c of f of x, right, f of x next to it, is equal to some value L, which is a y value, an output. This is read the limit as x approaches c of f of x is L. C being an X value, input L being a Y value. So if I come up here, both of these statements I can write using limit notation. I could say, okay, as x approaches 3, f of x approaches -1, the limit as x approaches 3 of this function f of x is -1. Even though f of 3 is either undefined, if this wasn't here, or if it was here, it's 1. This, even though f of 1 is 2, we would also say that the limit as x approaches 1 of f of x is also 2. Okay. Now that's limit notation. We also have one-sided limits and its notation. We will have what we consider a left-hand limit and a right-hand limit. Left-hand limit is LHL for short. Right-hand limit is RHL for short. The notation for a left-hand limit is that under case LIM as x approaches c. But what I will do is I will put an exponent above c that is a negative sign. And then the other stuff of f of x is equal to L. This is read the limit as x approaches c from the left. So what we will be doing is we'll be focusing on input values just to the left of my actual C value that I'm kind of focusing on. So I'll be looking at C values that are a little bit less than the actual C. That was interesting. The right-hand limit notation is LIM x approaches C, but with a plus sign in the exponent above C of the other stuff. It's read the limit as x approaches C from the right. We'll be looking at values a little bit bigger than the actual input that we're focusing on. And let's get another example up here so you know what this left-hand limit and this right-hand limit are and how they could be different. Here's a second example. I'll use this example a couple times. So go ahead and sketch this down if you wish. This would be considered a piecewise function. We have a piece defined to the left of 1, and then another piece defined at 1 and greater than 1, or to the right of 1. Now let's first talk about g of 1. So the function value at the input 1. Well, we have a closed circle and an open circle. It doesn't mean we have two function values, definitely not. We only have one, it'll just be the location of the closed circle. All of those points on those lines are closed circles, but they put it, they define it and they make sure there's a circle there at 1, -2, just so you know, hey, we're starting at 1, -2 and moving on with that second piece. So g of 1 is just -2. But let's talk about the limit around 1. Let's talk about the limit as x approaches 1 from the left of this function. This is what I'm going to be doing. Knowing that this 1 is an input, it's an x value, I'm going to be thinking about 1 and just to the left of 1 on my x-axis. And what I will be doing is I will find out where my function values are defined just to the left of 1. Well, to the left of 1, we're down here. And what we're going to do is as we approach 1 from the left, so we're getting really, really close to 1 as the input from the left, what is my function doing? Well, my function here is at -3, and it's staying at -3 to the left of 1. So I would say the limit as x approaches 1 from the left of g of x is -3. But in this situation, if I look at the limit as x approaches 1 from the right of g of x, let's see what happens. So 1 from the right, remember 1 here is the x value, so I'm looking at my x value. I'm looking at inputs a little bit greater than, so just to the right of 1. And what I'm doing is, as I'm getting closer and closer and closer to 1 from the right, what are my function values doing? Well, they're right here, and they are decreasing, and they are approaching this top value, -2. Now, if we went back to our first example, it's easy. The limit as x approaches 3 from the left, well, from the left of 3, my function values are approaching -1. And from the right of 3, my function values are also approaching -1. Which is why I can comfortably say that the limit as x approaches 3 is -1. Or if I asked you what the limit was in general for g of x at 1, you'd say, I don't know, it could be two things. It could be either -2 or -3. Turns out this limit in general does not exist. The existence of limits is what we'll talk about next. Limits only exist if the left-hand limit and the right-hand limit are the same. If and only if IFF, the left-hand limit is equal to the right-hand limit. Which is equal to some value. Using notation, limits exist if and only if the limit as x approaches c from the left equals the limit as x approaches c from the right, which is equal to some y value L. Mr. Olin.
So are you saying that the problem we just did above doesn't have a limit?
Yes. What I'm saying, what we are going to next, is that this problem up here if I asked you what the limit was at 1 in general, and if we go back to the existence of limits, I'd like you to throw in limits in general. I like the word in general here. Exists if the left-hand limit is equal to the right-hand limit. But if we look at this previous example, the left-hand limit was -3 as x approaches 1 from the left. The limit as x approaches 1 from the right was -2. So we would say that the limit in general as x approaches 1, notice no left or right, it's just in general, of g of x does not exist. The function value exists, the left-hand limit exists, the right-hand limit exists, but the limit in general does not exist. Okay. Going back to this one, we said it before. As we approach 3 from the left, my function is approaching -1. For approaching 3 from the right, my function values are also approaching -1, which is why this limit equals -1. And I don't have to always look at locations with holes or jumps. I could have done the same thing at 1. As x is approaching 1 from the left, my function is approaching 2. As x is approaching 1 from the right, my function is approaching 2. And in this situation, f of 1 is 2. So typically, limits exist for regular functions that don't have any crazy features, like holes or jumps or asymptotes. They'll just exist everywhere, and they are the function value. But we will be talking about certain cases when they're not. Okay, so maybe write that a little note. Limits typically exist and are equal to function values. i.e., the limit as x approaches 1 in this situation is 2, which is the same as f of 1. Not always, but most times. If you just have a smooth curve, your limits are going to exist. It's going to be equal to the function value. Yes? So limits can exist and function values if you have a sine curve. Or a straight line, or a parabola, cubic, quad, yeah, anything. Doesn't matter what it looks like, as long as it's continuous. I'll talk about continuity.
You can choose any point along a graph to be a limit.
I can choose any point and say it has a limit. So at 2, here's a point, the function value is here, and the limit is equal to that function value. However, here, the function value doesn't exist, but the limit does exist. In the previous example, the limit does not exist because we're not approaching the same thing, but a function value exists. Okay? So let's see if you guys pick that stuff up. We're going to do a big example with different scenarios. I'm going to see if you can get the right answers for these 9 problems. No, 16, 12. I wanted to go around it, and now I'm on it. Okay, you have 12 quick examples. You don't have to copy this down, but just look at it and maybe write down the correct answers. Try to do it by yourself. If you can, excellent. Then check with a neighbor. If you're trying and you're struggling, give it a couple minutes, struggle through it a little bit more, and then ask for help from your neighbor. Talk to your neighbor through these, okay? So ready, set, let's see if we can do this. Okay, talk it through with your neighbors.
But if they're equal. But I don't know. Yeah, I don't know. I don't come from the right of me.
The last ones are always the same. These two are always one.
I'm not sure. What do you do? Can you come from the left for an F is 1 because it's an open circle?
So for 1?
Yeah.
Yes. So go just to the left on the x-axis of 1. So you're just a little bit to the left of 1. Do you have function values above or below?
Yeah.
There. Okay. Are they up or down? Up. Okay. So we're tracking that piece of the function. And as we get closer and closer to 1, what we're approaching 4.
This one, there's no.
Exactly.
A little bit from the left, you go like 5. Okay, so you come a little bit from the right. Oh no, I'll put all my
You're going to struggle on the quizzes then, Mr. Gibbs.
That's why usually I try the homework with my tutor, and then I learn that way, and then
I feel like you're capable of getting this stuff. Don't rely on others. All right, here we go. Let's see if we got it. I'll start with the function values. F of -4. Well, I go over here to the input of -4. I look for my function value. I see an open circle. So even though it says -4, 2, that's kind of just telling me the location of the open circle. Since I have an open circle, it's undefined. But that was confusing because of the point. F of 1. I look at the input, x of 1. I look above and below. I see I have a closed circle above 1 at 4. So there's that function value. F of 6. I look above 6. I see we have this 0.65. However, there's an open circle, which means my function is not defined there at 5. It is defined at the y value of 2. Okay, so we start with that. Now let's just do the top row. F of -4 is undefined. If I look to the left of -4, are we approaching a specific value? Well, if I'm going just to the left of -4, my function values are right here, and they're increasing, and they're getting really, really close to 2. So if I had this in my calculator and I plugged in -4.000001, I'd get a y value that's probably like 1.99999. So this is 2. If I look at -4 from the right, so values like -3.999, and if I get really, 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 really close to -4, my function values are approaching 2 as well, which means the limit in general exists and is equal to 2. Now the next row, we see we have a jump. Well, if we look as x approaches 1 from the left, so here's 1, I'm to the left of 1. Where are my function values? They're up here. So as I get really, really close to 1 for my inputs, my y values are getting really, really close to this top point here at 4. So this is 4. If I look at 1 from the right, if I'm to the right of my input at 1, looking at my function values, as I get closer and closer to my input of 1 from the right, my y values get closer and closer to that y value -2. Since the left-hand limit and the right-hand limit are not the same, this limit does not exist. We would say the LHL does not equal the RHL. And then we look at 6. Well, the function is defined at 2. However, as I'm approaching the input 6, so I get really, really close to 6, I see I have function values that are getting really, really close to this y value of 5. So even though I have this 0.62, my function values look like they want to go to 5. So from the left, we have 5. From the right, it's the same way. Just a little bit to the right of 6. My function values are approaching this y value of 5 as well. So in this situation, my limit does exist and is equal to 5, but it's not equal to my function value. Questions? Sir?
What's the difference between does not exist and undefined?
So we use does not exist for limits. We use undefined for function values. So a limit can either exist or can't exist. You use that. Function values are either defined or undefined. It's just kind of the different terminologies used. Yes?
So we know there's a value for it, we just don't know what it is.
For -4, f of -4, no. There is no value defined at -4.
But there could be a value there?
There isn't that I can see. Unless for some reason there's some dot all the way down here that we can't see. It's not displayed on the graph, so no values, undefined. Other questions? Okay. Let's look at another problem like this. Instead of where do limits not exist, we can ask where do limits exist. You'll have problems like this on your homework. Where do limits exist for this function f of x? Anybody? Exactly. I like how we said everywhere except for 2 places. If I gave you a point like here, you say, okay, my function value exists, and we are approaching the same value, the limit exists. So typically, like I said, function values are the same as limits. Or the limits are equal to function values. If we have a function value, we'll be approaching that value from the left and the right. However, we don't have a limit at -2. The left-hand limit is going to be equal to -1. The right-hand limit here is going to be equal to 3. Over here, the left-hand limit is staying on this top piece. That'll be equal to 1. The right-hand limit over here is going to be equal to -2. That means the limit does not exist at -2. The limit does not exist at 2. So where do the limits exist? We would say all x's such that s dot t dot x does not equal -2 or 2. Okay? Now, let's look at not just the graphs of random functions. Let's look at functions defined by expressions involving x. Hopefully we'll be able to do that. Sweet. I feel like my computer is moving slowly. Okay, let's look at functions using expressions involving x, like this function x cubed minus 1 over x minus 1. Well, we can use our calculator to figure out some limits if I'm giving an equation for this function. So if you have your calculator, break it out. You can go ahead and graph this x cubed minus 1 over x minus 1, and you can see what it looks like. Looks like a quadratic. Looks like a normal parabola. Well, if I ask you to find the limit as x approaches 2 of this function, x cubed minus 1 over x minus 1, what are some ideas on how to find that limit? Should I start calling on random people? No? Not yet? How can I find the limit as x approaches 2? So on paper, we just kind of looked at where the graph was, we kind of looked where the y values were, and we said that's good. Can I do that on my calculator? What do you think, Mr. Thomas? Yeah, maybe let's go into our table and let's see what the function values are. Well, I see that when x is 2, the y value is 7. Now, Mr. Thomas, are you confident that we are going to be approaching that value from the left and from the right? Good, I am too. If I look at the graph and I see 2, 7, I see we're approaching that value from the left and the right. Our function value exists, equal to 7, and the limit would equal 7. And that's as simple as just plugging in 2 into my function and getting an output of 7. Typically, limits exist and they're equal to just the function values. If I wanted to, just to confirm that, I could have pressed the trace button, gone to an x value of 2. After you press trace, you can plug in whatever x value you want. You see we have the 0.27, input of 2, output of 7. We are approaching that point from both sides. Now what about for when x is 1? Let's go back into our table. I see when x is 1, we have an error. Well, that's interesting. Why is that? Because it's undefined. Because when I plug in 1 into this function, I get 0 over 0, which is undefined. Turns out, if I graph this, what would happen is instead of this being a smooth parabola, we would have an open circle here at 1. Well, does that mean the limit doesn't exist? No, the limit will exist. We can kind of look just at the graph and say to the left of 1 and to the right of 1, we are approaching some value. Question is, what is the value? Ideas on how I could find out that value. How can I find out what we're really close to when I get really close to 1? What do you think, Mr. Wolf?
You can trace 0.99 and 0.101.
It's a brilliant idea, Mr. Wolf. Why don't we just, instead of plugging in 1, which will tell me nothing, why don't we go close to the left by plugging in 0.999. I get 2.997. And I'll go close to the right by plugging in 1.0001. And I get 3.0003. Well, what do you think that location of the hole is at? I think it's at 3. So we say we do have a limit, even though the function is not defined there, but the limit is equal to 3. Now, there's going to be a piecewise example I'm going to do after the bell rings that you need to watch to do your homework for. But before you go, there's one more thing to talk about, and that's when we're talking about asymptotes. Let's look at 1 over x right before you leave. 1 over x looks like this. We could say the limit as x approaches 0 from the left, so approaching 0 from the left of 1 over x is approaching negative infinity. We could, however, I said in the definition of a limit that you have to approach a value. Negative infinity is not a value, it's more of a concept. So if you see an asymptote, even if both of these kind of tails trended in the same direction, like this, even though this would be positive infinity, this is like 1 over x squared, and if I look from the right, it would also be positive infinity, I would also just say that no, it does not exist, because we are not approaching a specific value, L. Okay? There's one more example you should watch on the video. I'll see you guys on Friday. Last example, we have piecewise functions we might encounter. We are asked to find the limit. Okay, the limit as x approaches 2. Well, we might as well also find the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. Because after we figure that out, we'll either know if the limit exists and is equal to a value or does not exist. The best thing to do with piecewise functions is to graph them. Now, let's remember how to graph. We just take x values, wherever x's are defined, and plug it into our function, our expression, to get our function values. So, example, if I wanted to figure out what f of 0 was, I'd plug in 0 into the piece of my function where x is defined. So that would be here when x's are less than 2. I get 3 minus 0 after I plug it in, which is 3. So that is a function value. I can do f of 1, which would be 3 minus 1. And that is equal to 2. And now what happens is I get really, really close. And let's go ahead and start graphing. So f of 0 is 3. F of 1 is 2. Okay, as I get closer and closer to 2, I'm still going to be following this function. So I could be plugging in like f of 1.999, and I'd get a value, which is 1.001 or something. Maybe there's another 0. Anyways, I'm going to get really, really close to, and eventually I will just stop using this function at 2, and I will pick up this one. However, I'd like to note where this function drops off, so where I can, end this. So I notice that we have a straight line. We saw that that's 1.001. Well, if I just plugged in 2, 3 minus 2 would be 1. That'd pretty much be where we stopped at this point, 2, 1. Okay, so that is my first piece. Now my second piece is defining my function at 2. So if I wanted to do f of 2, I'd plug it into the second piece. 2 squared minus 6 would be negative 2. So f of 2 is actually going to be negative 2 down here. Now we can keep going. F of 3, that's going to be 9 minus 6, or 3 squared minus 6, which is 3. So we'll have a point up here. And since it's x squared minus 6, we assume it's going to be a quadratic. That's going to kind of be increasing like that. So here's my piecewise function. Now, we should be able to see if our limit exists at 2. It does not. The left-hand limit, so 2 from the left, is different from the right-hand limit, 2 from the right. The limit as x approaches 2 from the left is 1. As we are approaching 2 from the left, my function values are approaching this hole at 1, which is why f at 1.999 is 1.001. But if we look at 2 from the right, here's 2, a little bit to the right of 2, my function values are approaching -2. Which means the limit as x approaches 2, in general, of the function does not exist. Does not exist works for limits, undefined values for functions. Let's do one more. We have the square root of x minus 4 if x is greater than 4, and 8 minus 2x when x is less than 4, which means we do not have a defined function value at 4 because we are never told what function to use when x is equal to 4. Okay, so instead we just have these two pieces. So let's start at 4. And I'll talk about when x is less than 4. So if I have like 0, we're at 8. If I have 1, we're at 6. If I have 2, we're at 4. I'm at 3, we're at 2. If I'm at 4 here, well, as I get closer and closer to 4, my function values are going to approach 0. So we'll have an open circle there right over 0. Now if I pick up here, where x is greater than 4, if I plug in 4 here, well, we're going to start back off on this 0. But I plug in 4.001, I'm going to be at like 0.001. If I plug in 4.002, be similar, be close to 0. I could plug in values like 5. If I plug in 5, I get 1. So all of a sudden this would pop up and go this way. So what I notice is that even though f of 4 does not exist or is undefined, is what I mean to say, because we do not have any inputs that is defining the function at 4. We don't have an equal sign underneath one of these. What we do have is a limit, because the limit as x approaches 4 from the left is equal to 0, and the limit as x approaches 4 from the right is also equal to 0. Okay, so that means the limit in general as x approaches 4 is equal to 0. Now, that kind of tricked me, actually. I was thinking it's 4. Here's a 4. So we did that problem. But here's another problem. What is the limit as x approaches 2 of f of x? Well, let's think. As x approaches 2, my function is approaching, okay, we're just worrying about this side, this piece of the function. As x approaches 2, my function is approaching 4 from both the right and the left. Okay, so that's it. We talked about asymptotes. We talked about everything else. Thank you. Come in with questions.